So hello everyone. Today I'm going to share you information how we prepare Kubernetes clusters, why we run Kubernetes in Kubernetes, and how we actually do that with Kamaji, KubeVirt, and Cluster API. A few words about myself. I started my Kubernetes experience working for Vedas. This is biggest Czech hosting company. We did amazing things like putting servers into the oil, and I was automating the deployment of those servers. So there were about hundreds of the servers, and I bring storage there and automation for those servers. Then I switched to work for Pelerg. We were developing Kubernetes platform. I brought virtualization based on KubeVirt there and storage as well. And since 2023, I founded the company who provide end-to-end solutions for data centers. And the main product is Cozy Stack. This is open source platform which allows you to run Kubernetes clusters, database as a service, and services like that. And the first question, do you like using Kubernetes in cloud? I guess yes, but there is all joke that there is no cloud, just someone else's computer. So today I'm going to share information for how to build this stack under the hood. Because if you use Kubernetes in cloud, you usually work with the very top level of the Kubernetes. But you don't actually care about the virtualization stuff, about bare metal servers provisioning, how to update those servers. I know kernel modules, bugs, and managing of all of this stuff. So today my presentation is more about this stuff. How can you organize your own Kubernetes hosting using Kubernetes for that. So when you work with Kubernetes in cloud, you usually see this scheme. So you have control plane separated, worker nodes, networking services, and storage. So everything separated. When you communicate with Kubernetes control plane, you can actually start deploying something there. You can automatically scale the nodes. You can scale them down or scale up. You can even actually remove all the nodes of your cluster, then create them again, and your application will start running and continue using previous data, so it will continue working. This scheme works very well, but what we do if we want to get Kubernetes on bare metal? When we're speaking about Kubernetes on bare metal, we usually think what if we will take some bare metal servers and install Kubernetes on them? Let's use some KubeSpray or K3s. There are a lot, or OpenShift. There are a lot of options. How can you do this? But instead of this beautiful scheme, you get something like this when you have everything in all together, and not every application is prepared to working in such Kubernetes cluster. By the way, it has no convenient management. The updates of such cluster usually quite painful if they're running some specific workloads which does not support that. And obviously it have no after-scaling if you have no proper bare metal provisioning and have no multi-tenancy. Kubernetes was always developed as such platform for not having hard multi-tenancy like OpenStack does. It does support some multi-tenancy opportunities like splitting users by the namespaces, but it does not provide you such hard level multi-tenancy and isolate tenants using virtualization, let's say. So when you're trying to solve such cases, you come to the idea that you need to have separated Kubernetes cluster for your customers, for your developer teams, and you start thinking, how can I do that? And you think, why should I install Kubernetes on bare metal servers? Why not use some cloud platform, let's say OpenStack for that? And then we can start provisioning Kubernetes clusters in OpenStack using Magnum or something like that. But there is a good question, who is responsible for OpenStack? OpenStack itself is a very complex system. It might be really painful to update it, and actually to support it, you need to have separated development team which will continuously developing, patching OpenStack and preparing the updates. Some companies run OpenStack inside of the Kubernetes just because of that. But I can say that nowadays Kubernetes is already prepared and has everything needed if you want to run Kubernetes clusters inside of the Kubernetes. So actually, in this layer, we can replace OpenStack with one big management Kubernetes cluster and run multiple small clusters for your users in this management Kubernetes cluster. Here, I will put two terms, so which I will use in the presentation. We call management cluster the Kubernetes cluster deployed on the bare metal nodes, and we have tenant Kubernetes clusters, which we give to the users, which are deployed inside of this Kubernetes cluster. What are benefits of this theme? You have same ecosystem, so you can use the same configuration tools like Helm, Argo CD, Flux CD, let's say. You can just use the same tooling. You have same ecosystem. You don't need to increase your cognitive load for managing it and cognitive load of your teams. It does support multi-tenancy. Since we have separated Kubernetes cluster, user can have full admin privileges there. They can install operators and custom resources, do whatever they want. They will be separated and separate virtual machines. And finally, those small tenant Kubernetes clusters, they implement the same cloud pattern like you have in original clouds, where we have everything separated: control plane, persistent volumes, and load balancing. Management cluster still looks like this, but we limit it to be responsible only for specific certain workloads which we know that they are working fine in this scheme. Actually, this cluster is responsible for run virtual machines, other Kubernetes clusters, and databases as a service. Such way, we decided to go and create our own platform, actually to accumulate our experience for running all of these services. And this platform is fully based on Kubernetes. It is managed by Kubernetes API, and it has already pre-configured monitoring, storage, networking, actually all the stuff you needed to just start provisioning your own managed services. This is how it looks like. So we have this dashboard where you can see all the managed services. It's just like Apple Store, and you can install all the services you want to. They're backed by operators, and they have full lifecycle management. Every managed service here is having just a set of parameters which you can configure. We provide bare minimum of the parameters because sometimes you don't want to give users original custom resources so they can override image there or change some other settings to compromise the system. We hide it behind the Helm charts, and we created our own API server which shows those Helm charts as Kubernetes objects. So how does this work? Cozy Stack provides full infrastructure layer needed for provisioning services, and we split it to multiple layers. On layer 1, we have operating system and hardware, actually kernel and Kubernetes. And on top of this, we start provisioning additional services needed to implement the same scheme. Before you start provisioning Kubernetes, you need to have storage working, networking, and virtualization. So on this layer, we use LinStore. It's a storage orchestrator, networking system based on KubeVirt, and virtualization based on KubeVirt. Then we also ship it with pre-configured operators, cluster API, and monitoring services. And on final layer, you have this API where you can create virtual machines, databases, and Kubernetes clusters. For the layer 1, we use Talos Linux. It's such Kubernetes-specific operating system. It works like Kubernetes, so it has controllers inside. And it is fully configured through the Kubernetes similar API. You actually can configure it with a single YAML file. The rest stuff we deliver using Flux CD. And on top of this, we created our API server, which dynamically translates Flux CD resources into Kubernetes objects, which can be used by the normal users. So let's first talk about layer 1, Talos Linux. Talos Linux is a very cool system because it allows you to configure the machine itself with a single YAML file. This is how it looks like. So it includes two sections, the machine section, where you can specify settings for the machine itself, and cluster section, where you specify the settings for whole cluster. You need to have such config for every machine prepared. Machine section includes such options like either it's control plane machine or worker. It includes certificates, network settings, network interfaces, and disk to install. While cluster section includes the settings for Kubernetes components, let's say control plane endpoint, certificates for Kubernetes, and specific settings for the API server and various Kubernetes components. So you write such configuration and apply it in TalosCTL tool. It's very similar to kubectl, and your machines start working. We found that not many users understand how this logic works. It might be difficult to them to start working with that, so we prepared our own script to automate this, to prepare such ClickOps. It looks like old school Debian installer. So let's say you have 3 servers. We provide them our Docker images for DCP server and Pixie. Pixie server also includes prepared baked Talos Linux image with all the needed kernel modules and kernel versions. So, and additional script which you can run externally to configure those servers. So servers can be booted from this prepared image, and then you use this tool to create Kubernetes cluster and actually provision the Talos Linux prepare configuration. Inside of this, it looks like old school Debian installer, so it can find all the nodes on your network, where you can put your host name, disk to install, some network settings, click next, next, next. It will generate Talos configuration and apply it directly to the node. So in such way, you can prepare cluster very quickly. We also have another method which allows you to do that in declarative form. But we really like Talos Linux because it allows us to make stable base for all the REST components, because our lint store, let's say, whoa, sorry. Yeah, because our storage, let's say, lint store, it depends on some kernel modules. We use ZFS and DRBD for the replication. Also, AVN and Cilium we use, they depend on specific kernel versions, and we can be sure that it will be working fine in every bare metal server. So after you have the cluster, we need to deliver the components of the platform itself. And now I want to share how we actually do that. We give user the single YAML file which they can apply on the created cluster. It will create single container which contains Helm charts. And it also has small shell script which will create FluxCD installation on the same cluster. And then FluxCD will take all of these Helm charts from the container and deploy into the same cluster. That works perfectly, because if we want to update, we just replace this container with new one, and Flux just updates the Helm charts. So we can make normal versioning for this container and such way prepare a distribution for our platform. This way we deliver storage settled. It works with well-known technologies like LVM and ZFS. And if you need, it can also enable storage-based replication, which works right in kernel. As well, OVN. OVN is really needed stuff in Kubernetes if you want to run virtual machines. The problem of normal CNI plugins is that they're not prepared to running virtual machines, actually. OVN supports such features like moving IP address from one node to another, and also it can remember IP address for the virtual machines and MAC addresses, which is also very important. We use KubeVirt to span virtual machines. KubeVirt works such way that it creates containers with libvirt and virtual machine process running inside. This is very interesting scheme because the container in KubeVirt is just specific service entity needed to be running virtual machine. And KMO is just Linux process which can be running as any other process in the container. Also, we have a monitoring stack pre-configured. And in this way, we deliver all the system components, so all the operators who manage our managed services, KubeVirt, storage, networking. So we have this prepared layer to run the other services. And now I want to share how we actually run those services, because Cozy Stack provides you opportunity to run managed Kubernetes, databases, virtual machines, and even S3 storage. So anytime when you deploy some application, all the applications you see here is actually Helm charts. But Helm charts do not provide you full lifecycle management like operator do. Problem of operators that they are very different. So every operator is written in different language by different team, and they have very different spec. We wanted somehow to unify this to show it in the same format. We decided to use Helm charts because they also allow to specify some icons, definition, and we can actually create our own API thanks to Helm charts. But under the hood, they still deploy custom resources for the operator, so we not lose the management for full lifecycle management for the applications. This is how it looks like. So we have Helm charts, which are defined and deployed by FluxCD. And finally, we created our own Kubernetes aggregation API server, which generates dynamically all the resources for those components and defines them as Kubernetes objects. So in case if you want to deploy a virtual machine, you can do it from the dashboard, or you can use our API from our API version. And the spec you see here is just values generated from the Helm charts. You don't have to recompile and create custom resources for this because our aggregation API server do that automatically. And under the hood, it uses FluxCD. So for every application, we create Helm chart, which creates resources which are then managed by the operators. In case of database, we use various database operators. Here is full list, not full, just part of the operators we use for provisioning databases. We found them really useful. We also contribute to them a lot. So we found that we manage them on our side. And every time when you deploy database, you can actually create, let's say, Redis object. It will create needed resources, and then operator will manage it. In case of Redis, it will create Redis failover for spot-at-home Redis operator, also service to exposing it externally, and additional service for scraping metrics from this Redis. So every service already have some pre-configured settings for and alerts and dashboards or everything. User works with such kind resource, and under the hood, it creates just free resources to deploy the fully managed Redis service. In case of Kubernetes, the most interested part, why are you here? We use Cluster API. So Cozy Stack provides fully functional Kubernetes clusters. That means that we did load balancers working, persistent volumes, and as well cluster autoscaling. The control plane is created using Kamaji project. We can say that Kamaji is Kubernetes operator for provision Kubernetes control planes. So actually, control planes are running as pods on our management Kubernetes cluster, thanks to Kamaji. It does all the lifecycle management for Kubernetes control planes. And it also integrates well with Cluster API, so we can use Cluster API to spawn virtual machines in the same cluster and join them to Kamaji control plane. Let's say we have dashboard, user creates Kubernetes cluster, and then it managed by KubeVirt, Cluster API, and Kamaji. Under the hood, it creates cluster object, Kamaji control plane, KubeVirt cluster, and also every node group which user can specify here. It creates machine deployment, which creates also KubeVirt machine template and Kubernetes config template. All of these resources managed by such named providers, Cluster API providers. We have control plane provider, which is managed by Kamaji. We have KubeVirt infrastructure provider, which manages resources for KubeVirt. And we have Bootstrap provider. We use default one, Kubeadm Bootstrap provider, which actually go to the created control plane, a spot, and creates join token for Kubeadm, and then it generates secret for cloud init configuration for the virtual machines. So after virtual machines get booted, they can automatically join to the control plane. Machine deployment resource in Cluster API creates machine set. It creates machine. Then it creates virtual machine for KubeVirt. It creates VMI. And under the hood, it runs the pod. In this way, we use management Kubernetes cluster. We use Cluster API to spawn multiple tenant Kubernetes clusters in the same cluster. But there are still questions how to configure CCM for it, CNI plugin, and also Autoscaler. In this way, we use the same FlagCD. FlagCD allows you to configure, to create components in your management Kubernetes cluster, but also in tenant Kubernetes cluster. So you can feed to FlagCD, use external kubeconfig, and it will go to another Kubernetes API and deploy the cluster there, deploy the Helm chart there. In this way, we deploy such components as tenant control plane, cloud controller manager, CSI controller, and cluster autoscaler. Inside of the tenant worker, we deploy CNI plugin and CSI node. You can notice that CSI controller and CSI node running in separate clusters. That is done for a reason, and that we don't want user from tenant cluster somehow access API for the management Kubernetes cluster. This is how it looks like. We can go to the management Kubernetes cluster and run kubectl get pods. You will see the created cluster here. This is control plane. It consists of 4 containers, actually API server, controller manager, scheduler, and connectivity service. Connectivity service, it's also a specific service which needed to communicate, to establish connection from the control plane to the workers. Sometimes API server needed to connect workers. Let's say if you want to see the logs or enable some port forwarding. The same components running as Cluster Autoscaler, KubeVirt CCM, and KubeVirt CSI controller. And here are 2 virtual machines. They're also created as pods. So now we can get secret for this Kubernetes cluster. You can just download it from the Kubernetes, save it to kubeconfig, and then you can export it using kubeconfig variable. So now we will speak with the tenant Kubernetes cluster. If we run get node, you will see these 2 nodes created, and there is a set of components we delivered by FlagCD into the tenant cluster. What about multi-tenancy? As I said before, we don't really like when users have access to management Kubernetes cluster. For now, it's slightly different because we implemented API for the end users, but they can actually only interact with our own objects. Original design was that users have no access to management Kubernetes cluster, and you still can have this model. So we run all of these components externally, and user can interact their tenant Kubernetes API, start provisioning persistent volumes, services. They will magically appear, but they will not see the controllers, how the controllers provisioning it. And also, we have really fancy tenant model. So we implemented tenants very similar to how Unix works. So by default, we have tenant root, and you can create additional tenants. Every tenant has its own domain assigned, and if you create new tenant, it gets subdomain to the tenant domain. Under the hood, it runs Kubernetes namespaces. It also has specific services like etcd for storing Kubernetes data, tenant Kubernetes data, monitoring, ingress, and also we have cvit here. And when you create new tenants, you can say that you want to have separated isolation by etcd or separated monitoring stack. So when you deploy applications inside of these tenant namespaces, they automatically detect if tenants have this isolation, and if have no, they will use the service from upper tenants. By default, we have network isolation enabled, so you can go from up to bottom, but not from bottom to top. This is done by Cilium network policies. So we have flat networking. And finally, we get such scheme where we have all the environments are unified and reproducible. We have simple installation interface for the users who don't aware how the Talos works. And the platform covers all infrastructure stack needed to build a cloud. It's easy to extend, so you can write your own Helm charts to extend the project, the platform with your own resources. And we are open source. Since last time we CNCF project, we joined to CNCF Sandbox. We have some community, so join and give us stars on GitHub. Few links which I want to provide you. It's a link to Talos Linux, to Cozy Stack website, also a link to the Kamaji Kubernetes control plane provisioner, and few links to my articles on Kubernetes.io, where I describe how this scheme is working. Many thanks to my wife who designed this beautiful presentation. That's actually it. Now I'm ready to answer your questions. Yes, please. The question about performance. When you run virtual machines as a containers, it has no something specific performance leaks. So if you run virtual machines, or let's say, talking about performance, we can speak about various technologies: storage, networking, and virtualization. The containerization not adds additional performance for the virtualization because the Linux processes have such namespaces by default. All of them have. Storage also fine because we just use the same block device from the host device. It can just pass through it into a container, and virtual machine can just consume. And as about networking stuff, there might be some a little bit worse latency because we have chain of the interfaces as usual in Kubernetes, which joins the pod sandbox with host namespace. Would it be possible to run KubeVirt inside of management cluster? Yes, we do that. Manage? I didn't get question. Tenant clusters. Yes, the question is it possible to run KubeVirt inside of the tenant cluster? It should be possible. KubeVirt actually expects on virtualization opportunities. So the only thing you need to have nested virtualization enabled, and you can pass it through this CPU host mode, which in KubeVirt is enabled by default. The question is if we consider using vCluster to use lightweight virtualization method instead of KubeVirt. We were considering using vCluster, but for the different way. We want to create actually federation support, and we want to have one common API to manage multiple cozy stacks. So we were considering to use vCluster in such way, but we don't use it for the isolation because usually we work with ISPs and bank systems. They expect to have proper level of isolation. So they need to have virtual machines to not allow user running anything in their cluster, and that can affect the other tenants. By the way, the virtual machines we're running in management cluster, they run without any additional isolation. So they run not in virtual machines, they run in just pods and give us almost the native bare metal performance. Yes, please. Yeah, sorry, I just little bit missed that part. The question was if we're using KubeOV and Cilium in our management Kubernetes cluster and which actually CNI we use. On management cluster, we use KubeOV just in terms of provisioning IP addresses and enable this option for actually to control the traffic flow. And we use Cilium as kube proxy replacement and for policy enforcement in management cluster. Inside of the tenant cluster, we just use Cilium because we don't need to run virtual machines there. No, Cilium in tenant clusters and also Cilium running in chaining mode on management cluster together with KubeOV. Thank you. Yes, please.
Why do you choose Flux against Argo?
That's a good question. I actually like both products. Yeah, sorry, I forgot to repeat the question. Why do we choose Flux CD instead of Argo CD? I like both products, but I think that Argo CD is more likely for development experience. The developers like Argo CD, so you can just give them dashboard. They will start deploying something there. It works just fine. You can even cut them off from the Kubernetes API access. But in case if you want to deliver some system things, Flux CD works better in case of it supports all the Helm API. It supports lookups and various Helm hooks, which we use a lot in Cozy Stack itself.
Are you not afraid of problems that Flux CD cause? Because you know that Flux is not GitOps fully approach.
We also not using it as GitOps approach because for us, Flux CD is more likely engine for delivering our Helm charts. As you can see, we didn't use any Git repository, so we ship it as separated Helm chart museum inside of the cluster. And then Flux, after that, starts provisioning the Helm charts from that. We had some problems with Flux CD. We solved them by writing our own controller, which triggers Flux to reconcile every Helm chart when it's needed. And also we have a new tool just released. It's called Cozy PKG. It also implements the same experience, so you can use diff actually between the local state of charts and the deploy chart. It simplifies development a lot. Yes, please.
I have a question about storage in the tenant cluster. If you create a PV in the tenant, how does it look on the management cluster?
The question is how the storage works in tenant Kubernetes clusters, and I can answer that there are those things for both the storage and networking. When you create PVC in tenant cluster, it also provisions PVC in management cluster. Then we have specific KubeVirt CSI which passes through into the virtual machine. And as about the services, it works the same way. So when you create new service with type load balancer in tenant Kubernetes cluster, it creates similar service in a management cluster and also configures it to route the traffic to the virtual machines. Yes, please. It should be possible with Kamaji because it runs normal native vanilla Kubernetes control plane, so you can use normal kube-button join process to join your nodes to this control plane. But we currently don't support this in Cozy Stack. We have plans to add support for this maybe in Q4 or next year. Yeah, if you provision bare metal nodes, you still need to have some opportunity to run. You can't just reuse the storage. You need to have another one which will be running externally or at least run this storage in the same node. So bare metal is always slightly more difficult than running virtual machines. And that's our way how we actually provision it. Sorry, we have to finish. Or maybe we have one more question? No, okay.